Hi everyone, in this tutorial we'll try to explain what is meant by dispersion in optical fibers, and this is a very important subject because the two most important characteristics of an optical fiber that determine its information carrying capacity are attenuation and pulse dispersion. Typically, when we send the pulse through a standard step index fiber link, it comes out spread out like this. This phenomenon is what we call pulse dispersion. So again, dispersion is the broadening of the input pulse in time as it propagates through the fiber. Pretty simple, right? So, what are the effects of this phenomenon on data transmission? The data can be corrupted by dispersion. If we send a sequence of on, off, on pulses, it would start its life as an electronic signal with nice sharp edges, as in this figure here. These pulses are used to switch a light source, usually an LED or a laser, and the resultant pulses of light are launched into the fiber. Dispersion causes the pulses to spread out and eventually they will blend in together and the information will be lost. The larger the number of pulses that can be sent per unit of time and still be resolvable at the receiver end, the larger will be the transmission capacity of the system. So if the pulse dispersion is large, then in order that consecutive output pulses be resolvable by the receiver, the time interval between adjacent pulses has to be greater than a certain minimum value. This would then limit the number of pulses that can be sent per unit of time, and hence the information capacity of the system. So long story short, the smaller the pulse dispersion, the greater will be the information carrying capacity of the system. That's why in communication applications, one always tries to reduce pulse dispersion. One question you're probably asking right now is what causes dispersion in fibers? Let's imagine we launch two different rays of light into a fiber. Now, since both rays are traveling in material of the same refractive index, they must be moving at the same speed. If we follow two different rays of light which have entered the core at the same time, we can see that one of them, in this case ray A, will travel a longer distance than the other, ray B. The effect of this is to cause the pulse of light to spread out as it moves along the fiber, as the ray taking the shorter route overtakes the other. This spreading effect is called intermodal dispersion. One solution to overcome intermodal dispersion is to use what we call graded index optical fibers. The essence of the problem is that the ray that arrives late has taken a longer route. We can compensate for this by making the ray that takes the longer route move faster. If the speed and distance of each route is carefully balanced, then all the rays can be made to arrive at the same time, hence no dispersion. Simple, at least in theory. The speed of light in the core is determined by the refractive index. The solution to our problem is to change the refractive index progressively from the center of the core to the outside. If the core center has the highest refractive index and the outer edge has the least, the ray will increase in speed as it moves away from the center. The rate at which the refractive index changes is critical, and is the result of intensive research. A parabolic profile is often employed, but there are many others available in specialized fibers. This design of fiber eliminates about 99% of intermodal dispersion. Not perfect, but definitely big improvement. We can consider the core to be made of a whole series of discrete changes in refractive index, as shown in this figure. At each boundary, there is a change in refractive index, and the light ray is refracted slightly. Every time the ray is refracted, the angle of incidence increases. Eventually, the ray will approach a layer at an angle greater than the critical angle, and reflection occurs. It's important to appreciate that, in a real graded index fiber, change in the refractive index is smooth and continuous. It's not really arranged in layers as is suggested by the diagram. The result is that the light suffers an infinite number of small refractions and has the effect of making the light bend in the smooth curves we saw in the previous figure, rather than discrete steps at each layer. Unfortunately, intermodal dispersion is not the only cause of dispersion. A common fallacy is that a laser produces light of a single wavelength. In fact, it produces a range of wavelengths, even though it is far fewer than that produced by a light-emitting diode, the alternative light source. This is unfortunate as the velocity of propagation of a light wave in any medium, and hence the refractive index of the medium, depends slightly on the wavelength of the propagating light wave. Normally, as the wavelength increases, the refractive index of the medium decreases. Because of the slight variation of a refractive index with wavelength, if light containing many wavelengths is incident at an interface between two media, the angle of refraction will be different for different wavelengths. This effect is called chromatic dispersion. Although chromatic dispersion is generally discussed in terms of a single mode fiber, it does still occur in multi-mode fibers, but the effect is generally swamped by the intermodal dispersion. One interesting feature of chromatic dispersion is shown in this figure. The value of the resulting dispersion is not constant and passes through an area of zero dispersion. This cannot be used to eliminate dispersion altogether, because the 0 point only occurs at a single wavelength, and even a laser produces a range of wavelengths within its spectrum. But you should know that by fiddling about with the dimensions of the core and the constituents of the fiber, we can adjust the wavelength of the minimum dispersion point. Solutions to deal with chromatic dispersion exist, and one of them is the possibility of using dispersion compensating fibers. The concept is fairly simple. The link fiber is characterized by positive dispersion. That is to say, longer wavelengths travel more slowly in the link fiber. So the dispersion can be compensated for by using a fiber in which longer wavelengths travel faster than shorter wavelengths. That's it for this tutorial. I hope it was beneficial for you, and if you liked it, encourage us by pressing the like button. See you in the next tutorial.